Hi class, welcome back. Today we're going to discuss a summary of the curve sketching. So in this section we get to we get to use everything that we have learned so far in this chapter, and so we get to use all those techniques to describe the function, to describe the behavior of the function in this section. So this is an important section because we get to summarize everything that we've done. In addition, we get to go back and review some of the algebraic properties about for a function. So let's jump in. So the goal is to analyze and sketch a graph of a function, and so we have already here some guidelines. Determine the domain and range of the function, the intercept, the asymptotes, the symmetry of the graph, locate x values for f prime, double prime, either zeros or do not exist, and then use the result to determine relative extrema and points of inflection. So let me just sort of give you guys an overview of what we're going to be doing. So we're going to be using all that information to get to tell us how the graph is behaving, so that we're able to sort of to be able to sketch it. All right, so it does require, it's a very important section, very important section. So please make sure you guys go over this section a few times, and then we're gonna go over this detail problem. I promise that I will have a question like this in the exam, where you guys have to find all this information and be able to sketch it. It's a very important. I must put this question in the test. There's no option for that. That I can't. So I promise you there will be a question like this in the exam. All right. So let's begin. Let's analyze and sketch the graph of f of x. So first of all, let's talk about the domain of the function. And the domain of the function, as we've done before in algebra. So this is from algebra, from our first college algebra course. We know that we can find the domain of the graph by looking at the rational function by looking at the denominator. So this function will be defined everywhere except where this is equal to 0, except where this is equal to 0. So find the x values that makes the denominator be 0, and then those will be out of the domain, right? So that's what I did. I found those numbers by solving for by setting the denominator equal to 0 and solving for x. By using the square root property, we got plus or minus 2. So the domain for this function is all real numbers except x equals plus or minus 2. So I wrote this in the interval notation: negative infinity to negative 2, negative 2 to positive 2, and 2 to infinity. Then we're going to check whether this is symmetric or not, and if yes, and to what respect. So the way we check for symmetry, we're going to plug in negative x into the function. So plug in negative x in for x, and you guys can see how that did. What I did there, plug in negative x, because there was this was being square. This was being square, so this is negative x squared will be positive x squared. Same thing here. And so we end up getting just basically the same equation, right? So we end up getting the same equation. So what does that tell us? That this is symmetric in respect to the y-axis. So this is it's going to reflect on the y-axis, right? And then so now our next goal is to find the derivative. So we'll find the derivative, and you guys done this so many times. The derivative is going to be 20x over x squared minus 4 squared. How did we do that? Well, we'll look at the original function, and we did the quotient rule, right? Low d high, derivative high, right? Derivative high is going to be 2x times 2, so it'll be 4x, minus high d low, derivative low is 2x, square the bottom, and there you go. And then simplify. What I did here was I factor 4x, and I'm left with x squared minus 4 minus x squared minus 9. So I had to distribute the negative to both of them, and that's how we got negative x squared plus 9. Combine like terms, and that give us positive 5, because the x squares cancel each other out. So 5 times 4x gives us 20x. all over x squared minus 4 squared. And there you go, we found the first derivative. we're going to find the second derivative by using the same rule, low d the quotient rule. So it'll be low d high, derivative high, the derivative high is 20, minus high, d low, derivative low, so we have to use chain rule, bring down the 2, leave the inside as it is, and subtract 1, and multiply by derivative of the inside. Square the bottom, there you go. The square of a square is the fourth power. Then we realize that those two terms have a common factor of x squared plus minus 4. So, and they also have a common factor of 20, so I factor that out. So I factor 20 and the quantity x squared minus 4. Then I'm left with, what's left behind? One of the x squared minus 4 factors. And just for 4x squared. So that x, that 2, and that 2x are left behind, all over x squared minus 4 to the fourth power. So simplify this. Negative 4x squared plus x squared gives us negative 3x squared minus 4. Then and that's it, right? That's your second derivative. So that's my second derivative. I ended up factoring out the negative negative factor, and then that's how I got the negative 20 outside. So I factor the negative, very, very simple, right? Okay. Number 5. Let's find the x-intercept. So this goes back to algebra. How do you find the x-intercept? Well, the x-intercept is found from looking at the function, the regional function, and setting your y equals 0 and solving for x. So solve for x. Solve for x, right? So let's do that. Set the function equal to 0 and solve for x. The only way that this rational function will equal 0 is whenever the numerator equals 0. So I set the numerator equal to 0 and solve for x. So you see that over here, divided by 2. Then we're left with x squared minus 9 equals 0. Add 9 on both sides of the equation, and then apply the square root property, and that gives us plus or minus 3. So plus or minus 3 is the x-intercept. What about the y-intercept? The y-intercept is found whenever x is 0. And so we're going to find the value of y. The value of y, the way we're going to find it is by setting x equals 0 and replacing x with 0 and solving for y. Well, that's going to give us 2 times negative 9 is negative 18. 0 squared minus 4 is negative 4. And that gives us, simplifies to be 9 over 2. Again, we're looking at the regional function, right? This is just the regional function. Remember that this was done in algebra. So then, therefore, the y-intercept is y equals 9/2. Then we're going to look at the vertical asymptotes. We reviewed this in one of the sections before. And also, we know this from college algebra. So how do we find the vertical asymptotes when we're dealing with the rational function? We look at the denominator. So we set the denominator equal to 0. Excuse me. And we solve for x by applying the square root property. We get plus or minus 2. And there you go. For the horizontal asymptote, we have two options, right? We can use compare the degrees, which would have been the same. So therefore, the horizontal asymptote will be the ratio of 2 over 1, which is 2, right? Or we can apply the limit, and sort of what I did in this case, apply the limit. Because it's a rational function, we could have just jumped into one of the guidelines that we already discussed in the previous section. But I did it with a limit, so you guys can kind of practice that as well. So I divided by the highest, by the variable with the highest degree, so that was x squared. Divided this by x squared, divided this by x squared, and that's what we got. And then simplify that to be 1 minus 9 over x squared, 1 minus 4 over x squared, right? And this, as x goes to 0, as x goes to infinity, this is going to become 0, this is going to become 0. So we got 2 times 1 and 1 over 1, so that would be 2. And a similar case will be for the limit as x goes to negative infinity. But we can also use the guidelines, right? Then we follow the critical number. For the critical number, we know that you have to use the first derivative. So let's use here, let me write a note here, critical numbers, right? For the critical numbers, we use the first derivative and we have two options. We find them by looking when the derivative is 0 or whenever the derivative is undefined. So whenever the derivative is 0, this is going to give us, this will be the time where the numerator is 0. So we're going to set the numerator equal to 0, and that gives us x equals 0. So that's a possible critical number. Then we have the derivatives undefined, and that will happen when the denominator is 0. So we're going to look at the denominator and set it equal to 0, and that will give us x squared minus 4 equals 0, which will give us x squared plus 4, which gives us x equals plus or minus 2. Now I cross these two because they're not part of the domain. Remember that that 2 and negative 2 are not part of the domain of the function, of the original function, so therefore these cannot be critical numbers. Now they're not critical numbers, but they're still going to be part of the number line. We're going to discuss that later on. The next one is, so the only critical number that we have is x equals 0. So there you go. The next one is finding the possible points of inflection. How do we do that? Well, we look at the second derivative, possible inflection points, right? Possible inflection points. So for that one, we're going to use the second derivative, and we just mimic the same process that we did before. First case, when the second derivative is equal to 0, we look at the numerator. So we set the numerator equal to 0, and this cannot happen because what happens here is that this is a positive number. It's always going to be positive because x squared is always positive, multiplied by positive is positive, positive plus positive is always positive. So therefore, a positive number times a negative will never be 0. So therefore, this cannot. So this is not going to be equal to 0 ever. So there's no possible points of inflection from here. What about the second derivative being undefined? Well, that happens whenever the denominator is 0. So we're going to set that equal to 0, which is x squared minus 4 equals 0, which equals the same story that we've done before. It's going to happen whenever x equals plus or minus 2. But remember, again, the inflection point must be also part of the domain. These are not part of the domain, so therefore these are not inflection points. Now they can still be part of the they will still be part of the number line, as you guys will see in a second. So there's no points of inflection in this graph. Okay, what about testing the intervals for which f is increasing and decreasing? So that will be in this section. We're going to have to make a number line for this. So here's my number line. First, we're going to check whether it's increasing, decreasing. So this is my number line for increasing, decreasing. I use my critical numbers. My critical number was x equals 0, but then I also use the numbers that made the denominator be 0, right? So even though these are not critical numbers over here, right? Very important. Even though these are not critical numbers, they're still going to be useful in the number line because actually things can change in between those two. Things can change in those two. Not in this example, but you guys will see that in other examples they will change. All right, so you must include a negative 2 and a 2 in the number line. You're going to test every region that you have here. So I did the test over here, right? So here's my derivative. And I realized that the bottom part, the denominator will always be positive, so I made myself a mark. So I only have to test the top part. So the top part, whenever x is negative 3, then the top part will be negative, and the bottom part is obviously positive, so this will be a negative. So there you go, negative right there. Whenever x is negative 1, we're going to have the top will be negative and the bottom will be positive, so that will be negative. There you go. When x is positive 1, the top will be positive, the bottom will be positive, so therefore positive over positive is positive. And then bottom part is x equals 3, right? The testing number is 3, so positive over positive will give us positive. Now, if you guys notice, I did something special. I always do this in my notes. I write myself a note here. This is this was the critical number, and this is critical number whenever the derivative is 0. This was a possible critical number, and this was when the derivative was undefined, right? So I write myself a note, and then I write myself a note here also for the function. The function was undefined here. The function was undefined here, and then so that allows me to sort of give me a good description of what's going on. Now that I know the derivative is negative, that means the function is decreasing. When the derivative is negative, the function is decreasing. Derivative is 0, the function is horizontal. The derivative is positive, so the function is increasing. The derivative is undefined here, but the function is undefined as well. The derivative is positive, so the function is increasing here. So what can we conclude here? by looking at this, the function is decreasing from negative infinity to negative 2. Decreasing from negative infinity to negative 2, and from negative 2 to 0. There you go. The function is increasing from 0 to 2, and then from 2 to infinity. Notice that there is a discontinuation from there because the function is undefined there. So make sure that you are separating these intervals. What about concavity? So we'll do the same thing, but now with the second derivative. So here we go. Here we have a number line. We're going to separate this with our possible inflection points. So the only one that we had was negative 2 and positive 2, and these cannot be inflection, right? But they're still going to be part of the number line, right? And it's very consistent, right? Even though they're not going to be critical numbers or not going to be possible inflection points, they will be part of the number line. They will be part of the number line. So please make sure you put a note on this. We'll see what happens now. So now when we test the numbers, this is going to be negative 3, 0, and 3. We already know that the second derivative will be undefined for negative 2 and 2. And we know the function will be undefined for those values. So all we got to figure out is this, this, and this. And so we're going to use the second derivative, and we're going to go ahead and test these numbers, negative 3, 0, and 3. But we also know that on the numerator, we have that negative 20 will always be negative, and this will always be positive. So we have negative times positive will be negative on top. So we can make myself a note for that. That way I don't have to test that every single time. That will save me so much time. So pretty much only have to test the bottom part. So the top will always be negative. When I plug in negative 3, the bottom will be positive because this will give me 9 minus 4. So it will be a positive. Negative over positive is negative. When I plug in 0, this will give me, top will always be negative. So 0 squared minus 4 will be negative. Negative over negative is positive. When x is 3, the top will always be negative. So the bottom part will be positive. So negative over positive is negative. So we have negative, positive, negative. Now we know that when the second derivative is negative, the function is concave down. When the second derivative is positive, the function is concave up. When the second derivative is negative, the function is concave down. And so we have that the interval for which the function is concave up is negative 2 to 2. And where the function is concave down is from negative infinity to negative 2, and from 2 to infinity. And there you go, right? We sort of already used that information. We have summarized all the information. Now let's go ahead and graph this function. So my suggestion will be to start with the top information. First, let's talk about symmetry, right? We said that it's going to be symmetric with respect to the y-axis. So that means that it's going to be mirror. You're going to have a mirror from this side. It's going to mirror this side right there, right? So we should see a reflection there. Okay. So, and we see that, right? So what I'm saying by this is that by knowing that, you only have to work on one side, and you can copy the other side, right? That would be, or you can double check that everything looks good. Right, so let's see what's the next one. I'll say start with the asymptotes. So start with an asymptote. So here we go. So we had an asymptote at x equals negative 2 and positive 2. Perfect. We also had a horizontal asymptote at 9/2. So perfect. There you go. We already have those two. Now, what do we know about the graph? We have intercepts, right? We have one intercept, one x-intercept at negative 3, and we have an x-intercept at positive 3, right? According to our notes up here, negative 3 and positive 3. We also have a y-intercept at 9/2, so that means we're intercepting the y-axis at 9/2. So there you go. We already have 3 points. We already have asymptotes and 3 points. Now let's talk about the function. So what do we know? So according to our function, we already know that we have a relative min. We have a relative min. If you notice, we have a relative min at x equals 0. We can see that from here, right? We have relative min at x equals 0. So at some point here, this is going to turn around, something like this. We also know the function is decreasing, right? So the function is always decreasing. So it's always decreasing, and it has to be concave down. So therefore, that's gonna tell us that it's not gonna be here. It's not gonna be here. It has to be down here, right? Two things, because the point is down here. We already know the point is down here, and we know the graph has to be decreasing and it has to be approaching these asymptotes. We already know that it's gonna be looking like this, but we already know it's not gonna be this because it always has to be decreasing, right? It has to always be decreasing. So therefore, we already know how this looks like. What about the middle one? Well, we know that the middle one from -2 to 2, we have a concave up. So we know it's going to be like a U. And we know that it's confirmed here by the first derivative. And we know that's going to be at x equals 0, a relative min. So we already know that it's going to look like a U. So there you go. Now we can use the symmetry to say, oh, it's going to be the same thing over here. Or we can go ahead and justify it. We know this can be always going to be increasing from 0 to infinity. So from 2 also, from 2 to infinity is always going to be increasing. We know also it has to be concave down. So it would have been like this, but since we're always increasing, we're always going to stay closer and closer to that horizontal asymptote. And this is what I expect you guys to be able to show. In the test, I expect you guys to show me those points, to label those points, to label those horizontal asymptotes, to be able to graph this to this degree. All right. So wasn't that kind of interesting, right? If you guys think about this, we're able to describe the behavior of the function to a detail, right? It's so much detail that we found by exploring the algebra, by exploring the calculus part of it. All right. So we have a few more that we wanna practice. So here's another one. In this example, we're gonna sketch the function x squared minus 2x plus 4 all over x minus 2. So let's talk about domain. So the domain for this, we're going to do the same thing because it's a rational function. Let's look at the denominator. So where would the denominator be equal to 0? We'll make the whole thing undefined. So we're going to exclude the number that makes the denominator be 0. So we'll set equal to 0. We find out that that's when x equals 2. So when x equals 2, this will make the denominator be 0, which will make the whole thing undefined. So period. We're going to remove 2 from the whole domain. So from negative infinity to infinity, we're going to remove 2. What about symmetry? Well, let's check symmetry. So plugging negative x into the function, that becomes x squared. This becomes positive 2x plus 4 minus x minus 2. So this is not going to be symmetric because this is not going to give you back to the original function. This does not give you the original function, obviously, because it does not look like the original function. But even if you try to factor negative x from here, it's not going to look like the negative times the original function. So this is not symmetric. The first derivative. All right, so finding the first derivative of this will require for us to use the quotient rule. So this will be low times d high. So d high will be 2x minus 2 minus high d low, which is just 1. Square the bottom, and there you go. Use distribution. There you go. That will be 2x squared minus 2x minus 4x plus 4. And then here I distribute the negative, minus x squared minus plus 2x minus 4 all over x minus 2 squared. Simplified, and you notice that 2 x's cancel each other out. The 4 and the 4 cancel each other out, so we're left with 2 and the minus x squared cancels some of the 2x squared. So we're left with x squared minus 4x. Factor the x from here, and that way we have it in terms of a factor. So a lot of times we're gonna use this factorization when we're dealing with the critical numbers, but for now this is good enough, right? So I wrote my first derivative. Second part is find the second derivative of this using the quotient rule again. So we can use this part. So low d high, derivative of high will be 2x minus 4 minus high d low square. Derivative of low will be bring down the 2, leave the inside as it is, take away 1 from the power, and multiply by derivative of the inside. All over, square the bottom, there you go, right? So square the square gives you 4th power. From here, right, this is where the technique where we have to be careful. We have to factor x minus 2. So this factor x minus 2 from both terms. So factor x minus 2 and factor the x minus 2. So what's left behind? Well, if you factor an x minus 2 from here, then you're left with 1x minus 2 here with multiplied by this factor. So x minus 2, 2x minus 4. Factor in x minus 2 from here. What's left behind? The 2 times the 1 times this. So that will give us this right here. Also, I'm looking that we can probably factor in x minus 2 from the bottom, because we can see that those are going to cancel each other out. So those cancel each other out for the next line. Those cancel each other out. So what I'm going to have now is going to be distributing these two, right? So we end up getting 2x squared minus 4x plus 8 minus 2x squared plus 8x. And that simplifies to be, by looking at these, those cancel each other out. The negative 2x squared and the 2x squared cancel each other out, so we're left with the 8 all over x minus 2 cubed. So there's your second derivative. All right, simple. It looks pretty simple, right? Compared to what we started from. Who would think that, right? All right, so there's our second derivative. Now let's find the x-intercept. So to find the x-intercept again, right, what we discussed before is that would happen whenever y equals 0. So what we need to do is find the x value. So set the y equals 0, and that means the whole thing is going to equal 0. This is going to equal 0 only when the top equals 0. So we'll set the top equals 0. Try to factor this out. You try to use the quadratic formula. This will give you a negative value here, which means this will be an imaginary number. So we're not dealing with imaginary, we only deal with real numbers. So this is not going to be a number, an x-intercept. So therefore there's no x-intercept. What about y-intercept? The y-intercept happens whenever x equals 0. So that means let x equals 0 and find y. All right, and that would happen whenever we'll set x equals 0, so plug in 0 for x and solve for x. That will give you 4 over negative 2, which gives you negative 2, which gives you y equals negative 2. So that's your y-intercept. Vertical asymptotes. The vertical asymptote again happens when you're dealing with rational functions when the denominator equals 0. So look at the bottom and set equal to 0. That means it's x equals 2. Vertical asymptote is x equals 2. What about horizontal asymptote? Horizontal asymptote happens whenever the limit as x goes to infinity. Now we could use the guidelines, right? And we can say compare the powers, and we can conclude that there will be no horizontal asymptote because this one is higher than that one. Or you can just follow the limit, right? By dividing top and bottom by the variable of x. And that will give us x squared over x, 2x over x, 4 over x over x minus 2 over x. And then apply the limit as x goes to infinity. The top will go to, this will go to 0, this will go to 2, and this will go to infinity. And this will go to 1, and this will go to 0, so this is going to go to 1. So it will be 0, infinity over 1, which is infinity. And the similar argument happens when we're dealing with negative infinity. We're actually going to go negative infinity, right? So you notice, apply the limit here, apply the limit, same thing we did before, so we're going to copy paste this step to here. Now when you apply the x goes to negative infinity, this is going to go to 0, this is going to go to negative 2, but this is going to go to negative infinity. This is going to go to 0, and this is going to go to 1, so 1, this is all going to 1. So negative infinity over 1 gives you negative infinity. So there's no horizontal asymptote, but we know where this is going. What about critical numbers? Critical numbers, we look at the first derivative, and we have two cases, when the derivative equals 0 or when the derivative is undefined. So set the numerator of the derivative equal to 0 to find this case, and that would be x times x minus 4 equals 0. Do you guys notice how I use the factor 1? Because this is going to make it easier for us to find the zeros. That will be, after you factor them, you separate them, each factor to equal 0, and that gives you x equals 0 and x equals 4. So those are two possible critical numbers. The other ones will happen whenever the denominator is 0. So you set the denominator equals 0, and that will happen when x equals 2, but we already know that x equals 2 is not part of the domain. But not part of the domain, it's not part of the domain, so it's not a critical number, but it's still going to be part of the number line, right? It's going to be part of the number line. So the only critical numbers technically is x equals 0 and x equals 4. What about inflection points? For inflection points, we're going to look at the second derivative, and we're going to do exactly the same thing we just did, right? Do the second derivative equal to 0, but that's not possible because x cannot equal 0, so there's nothing here. There's no possible inflection points here. What about for the second case? That is when the second derivative is undefined. That would happen when the denominator is 0, which we know is going to happen when x minus 2 equals 0, which we know is going to happen when x equals 2. But x equals 2 is not part of the domain, so this is not a possible inflection point, but it's still going to be part of the number line. All right, so no inflection points here. What about intervals, testing intervals? Now, there's one thing that we want to discuss here. There was a, since the function did not have horizontal asymptote, have a horizontal asymptote, we still have to check one thing to make sure that there's no slant asymptote. There might be a slant asymptote, and slant asymptotes actually happen, you're guaranteed to happen whenever the difference between the highest degree of the numerator and the degree of the denominator is 1. The difference between those two powers is exactly 1. If the difference between those two is 2, excuse me, there's no slant asymptote. But because the difference between those two is 1, then there's a slant asymptote. What about if this is a 3 and this is a 2? Yes, there's a slant asymptote. So how do we find slant asymptote? We have to actually divide those two. So divide the numerator with the denominator, and we can use syntactic division in this case, because this is the case where you have x minus 2, right? Where this is simple enough where we can use syntactic division. So I use the 2 there, I use the coefficients there, bring down the 1, 2 times 1 is 2, subtract those 2 gives you 0, 2 times 0 is 0, so 4 minus 0 is 4. So this is the remainder, but this right here is your quotient. So the quotient part will be your slant asymptote. So in this case, this will be 1x and then plus 0, right? This is the coefficient of your x. And so therefore, your slant asymptote actually happens to be y equals x. Y equals x. So that's your slant asymptote. And then now let's find the intervals of increasing and decreasing. So how are we going to do that? Same thing we've done before. We're going to let the number line, we're going to create a number line, and we're going to use our critical numbers. Our critical numbers was x equals 0, x equals 4, and then we had a possible critical number, which is not part of the domain, which is x equals 2. So we have 1, 2, 3, 4 regions for us to check. We're going to use -1, 1, 3, and 5 to test. And we're going to use the first derivative, right? Because we're trying to find the information of the first derivative, only whether it's positive or negative. So again, let's try that. When I wrote my first derivative, I noticed that my denominator will always be positive because it's being squared, right? It's always going to be positive, so that will save me some time. So basically all we have to do is check the top. So when x equals -1, plugging the -1 to the first derivative, that's going to give us negative and negative. So therefore we have negative times negative is going to be positive over positive gives us positive. Plugging 1, that will give us positive 1, and that will give us negative. Positive times negative is negative over positive is negative. 3, plugging 3 here, plugging 3 there, that gives us positive and negative. So positive times negative is negative. That gives us negative over positive is negative. And 5, that will give us positive and positive, over positive gives us positive, which is positive. So we have positive, negative, negative, positive. So that means the function is going to be increasing, horizontal, decreasing, undefined, and then decreasing, horizontal, and increasing, right? So we can see here that we can already see that at x equals 0 and x equals 4, we're going to have a relative max here and a relative min there. All right, so let's summarize that part. We know the function is going to be increasing from -infinity all the way to 0 and from 4 to infinity. And that's what I have already here. What about when this is going to be decreasing? It's going to be decreasing from 0 to 2. Sorry, I made a mistake here. That should be a 2, and that should be a 2. All right, so from 0 to 2 and from 2 to 4, right? It's going to be decreasing, and then now let's talk about concavity. Let me fix that right there. That's a 2. There you go. All right, so now the next one would be whenever we're going to check concavity. So let's look at the second derivative, and we're going to test two numbers, 0 and 3, right? Now there was no inflection points, but there was one possible one that we needed to check. That was whenever the denominator was 0. It's not going to be an inflection point because it's not part of the domain, but it still needs to be used in the number line. As we can see here, we can see how that's going to affect the concavity. So let's go ahead and do that. So from here, we're going to test, we're going to realize that 8 is going to be always positive. So we already know that from we can make that note for ourselves. So all we have to do is check the bottom right. So when x equals 0, the second derivative will be positive over negative, right? 0 minus 2 is negative. So positive over negative is negative. When x equals 3, we're going to have positive over positive. So positive over positive is positive. So we have negative, negative, positive, positive. For f, that means that we're going to have concave down. And for this part, we're going to have concave up. Remember that what we said here is that if you have negative, negative, that would be sad face. Sad face. When you have positive second derivative, that would be a happy face. So look like that. All right, so there you go. So we're gonna have concave up from 2 to infinity. Concave up, right? The cave is facing up. It's gonna be concave down. The cave is facing down from negative infinity to 2. And there you go, right? So now we have all the information that we need to be able to graph our function. So here, this is how I would start, right? So let me just do, here's a picture, but this is how the process that I would have that I would do. So I'll start with first doing any intercepts. Do we have any intercepts? All right. I think my iPad is getting warm, so it's acting up right now. So we have one intercept, and that's at y negative 2. So at y negative 2, I'm going to have a point there. There you go. Now we also have a vertical asymptote at x equals 2. And then we also have a slant asymptote that is diagonal. It actually behaves like y equals x, right? It's a diagonal that has a slope of 1 over 1. So that means that we're going to have a slant asymptote. Let me write these in blue. Draw this in blue. That way we can see the difference between a graph and an asymptote. There you go. So this is y equals x. So now, what else do we know? We know that the function is going to be concave down on the left side of 2. So we know this has to go like this, and we know that this has to go like this from this side. Now it could be up here, but if you guys notice, if we have this, then this is going to be concave. This is concave up, and we already know it's supposed to be concave down. So we already know that it has to be concave down on the left side of 2 of x equals 2. So we know that it's going to be in that form, and we also know that the function is it's increasing and then decreasing. So followed by increasing, and then we know that at x equals 0, we have a relative max. So from here, that's the highest point that we can get. We already know that because of the inflection, because of the first derivative test right here, right here. This tells us that we have a relative max at x equals 0. So therefore, we already know that this is going to be the highest point, and so we're going to head down from here. There you go. Right. What about over here? We also know that at x equals 4, we have a relative min. So maybe that would be worth for us to find what is the value of at x equals 4. So on the function, what is that value? Well, if we plug in 4 into the function, we're going to get 16 minus 8 plus 4 over 4 minus 2. That will give us negative 4. That would be 12 over 2. That gives us 6. So 6 is going to be a relative min. And so at x equals 4, we're going to have 1, 2, 3, 4, 5, 6. So somewhere around there, we're going to have a relative min. And it's going to look like this, right? And it matches our graph. There you go. And we're going to label our points. So this point is going to be 4. Let me put this in 4, 6. And this will be 0, -2. And there you go, right? We're able to graph the function. And there you go. So we're able to graph the function to a degree of detail. All right. So let's find the next one. So this one is interesting. We're going to be able to do the same thing, sketch the graph of this radical function. This is a radical function because it has a radical piece in the function, right? So which is the denominator. So let's start finding the domain of this. The domain of this is going to be actually all real numbers. Because if you guys notice, the only way that this is going to be undefined is whenever the denominator is 0, but also when the radicand is negative. But this is always going to be non-zero, right? This is never going to be equal to 0, and it's never going to be negative for the radicand. Why? Why is that true? Because let me fix that right here. Because this is always positive. How do we know that's always positive? Because x squared is always a positive number. So the least that this can be would be 0, right? And if this is a negative number, the square is going to make it positive. And so you're adding a positive to another positive, so that makes it always a positive number. So you're never going to have the square root of a negative number or the square root of a 0. So no matter what x is always going to turn out to be a defined value. So this is going to work for every single x value. So it's going to go from negative infinity to infinity. For symmetry, we're going to plug in negative x. We're going to plug in negative x. And what we see here is that the negative x, when plugged into the top and the bottom, we can factor the negative to the front, and then the square in the denominator is going to make it a positive. So this is just looking just like the original function, except that it has a minus in front of it. And then so when this happens, actually this suggests that this is symmetric to the origin. So therefore now we're going to use that information later, but now let's find the first derivative. To find the first derivative, my suggestion is to write the function in terms of power form and apply the quotient rule. So it'll be low d high, derivative of high will be just 1 minus high d low, derivative of low will be bring down the power 1/2, multiply by derivative by the inside function, subtract 1, and then multiply by derivative of the inside. And then square the bottom, and there you go. Well, because this is a square root, when you square the square root, that becomes a 1. So now the next part will be to simplify this. So I would suggest you guys factor x squared plus 2 to the negative 1/2 because they're both common factors there. So when you do that, then you're left with behind by a 1 factor of this minus after you remove this whole thing, you're left with 2x times 1/2 times x, will just be the 2's will cancel it out, and the x will give us x squared. Now if you guys notice, why is it just 1 right there? Well, remember that this added to this should give you this. So because when you multiply these two together, the powers should add up to be this number, this power. So negative 1/2 plus 1 gives you 1/2. By doing this, if you guys notice, everything is so simple now. We can actually simplify this much easier. X squared minus x squared cancel each other out, leaving you with 2. This will go to the bottom part, right? So it becomes a positive power. When you multiply this positive power on the bottom, it becomes positive 3/2. So there you go. So we have that, or you can write it also as negative power. Why do I write it as negative power? Because it's going to help me find the second derivative. So let's try that. When you apply the second derivative for this, I'm going to use chain rule. So it'll bring the power down, so it'll be negative 3/2. Leave the inside as it is, take away 1 from the power, and then multiply by derivative of the inside. Well, that's going to become these two are going to cancel each other out. This 2 multiplied with this will give us negative 6x, and then this has negative power, so we're going to put that on the denominator. And so that's how we got this negative 6x over the quantity x squared plus 2 to the 5th halves. Alright, so that's the second derivative. We're going to find the x-intercept by setting y equal to 0 and finding x equals the value of x. Alright, so we're going to let that be x. So we're going to let y be 0 and solve for x. So we have this quotient. Remember that the quotient is going to equal 0 whenever the numerator equals 0. So that is when x equals 0. So for the y-intercept, it would be whenever x equals 0, solve for y. And so we're going to get, that's going to happen. That's going to simplify to be 0 over 0 squared plus 2 to the 1/2. And that's just going to be automatically 0, so that gives us y equals 0. So there's only one intercept here, and that happens at x equals 0, y equals 0. What about vertical asymptotes? Vertical asymptotes would happen whenever the denominator is equal to 0, and we are going to set the denominator equal to 0, and we're going to realize that this can never equal 0 since this is always a positive number, so there's no vertical asymptote. What about horizontal asymptote? Well, when we try a horizontal asymptote, because it has a square root function underneath, then we can use the guidelines that we have used for the powers. So we have to use the long way. So we're going to apply the limit as x goes to infinity, right? But first we got to take the numerator and the denominator divided by x. Why x? Because this is the highest, the variable with the highest power. How do we know it's just x? Well, think about this. If we remove this, right, this will help us see it. So it'll be x squared to the 1/2 is going to be x to the 1. So divide both top and bottom by x. So that'll be x over x. But on the bottom part, it actually turns out to be x is the same thing as x squared when you push it into this radical. Just like the example that we used in the last section. So please refer to the last section for this. So x squared over x squared plus 2 over x squared. When you simplify this, will give us 1 all over the quantity 1 plus 2 over x squared to the 1/2. As x goes to infinity, this will give us, this will turn into a 0. So we have 1 over 1, which gives us 1. So the horizontal asymptote will be 1. When you try the negative part of it, which you should because this is our square root, you guys will see here that we had to use a different value. We actually had to use 1 over negative x, because remember that x is approaching negative infinity. That means that x is naturally a negative number. So this is a negative. The x by itself is a negative number. So I have to put a negative in front of it to make it a positive. Why do we need to make it a positive? I explained that in the last section. So here briefly is because when you push this value into this square root, you got to make sure that you can use a positive number. So therefore, we're going to have x over negative x, x squared over x squared, 2 over x squared. Now, the negative goes away because when you put it in here, this turns into 1 over x squared. I explained that in the last section as well. So then this simplifies to be negative 1. This turns into be 1. And so when you simplify this gives us negative 1 all over 1 plus 2 over x squared to the 1/2. When you take this to infinity, this turns to a 0. So we have negative 1 over 1 to the square root of 1. It's 1. So negative 1 over 1 is negative 1. So therefore, we have a horizontal at negative 1. What about critical numbers? We'll do the same thing. Take the derivative. Set it equal to 0. That's not possible because 2 is never equal to 0, so there's no critical numbers for this part. What about when the denominator is 0? That will not happen because this can never equal 0, so there's no critical numbers. What about possible inflection points? Well, that would happen whenever the second derivative is equal to 0 or undefined. So here's the first case. So the second derivative will be a 0 whenever the top is 0, which means it's whenever x equals 0. So that's one possible critical number. What about it's going to be undefined whenever the denominator is 0, but we know that that's never going to equal 0. So there's no possible inflection points from here. So there's only one. Well, what about testing intervals? So testing intervals, we're going to use the same number line, right? And this number line, here are x values, here's the first derivative, and here's our function. There's no critical numbers, right? There were no critical numbers, so any number will be just fine to test, right? So we can see here also, in fact, is that the first derivative is going to be positive for the top and positive for the bottom. So positive or positive will be positive, so we know this is always going to be positive. So we have positive, 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 so the function is always increasing. What about concavity? So here's a number line. For x's, we have x equals 0 to be the possible inflection point, and the second derivative happens to be 0 there, right? 0 is for x equals 0. So we're going to test -1 and 1, right? Just random points on the left and the right, -1 and 1, and so we're gonna realize that the bottom part is always going to be positive. So basically all we have to do is test the top part. So when plugging -1, we got -1 times negative becomes positive. So positive over positive is positive. When plugging a +1, we get -6 times 1, which is negative. Negative over positive is negative. So positive, positive, negative, negative. So we know that the original function will be concave. Sorry, I think I missed here. Sorry, let me fix this. This will be concave up, and this will be concave down. There you go. There you go. So so we have that the function is going to be increasing, right? So conclusion, f is going to be increasing from -infinity to infinity. There's no decreasing part. Concave down from let me fix this. There's going to be concave up from -infinity to 0, and concave down from 0 to infinity. All right, there you go. And so now this will help us graph the function. So here we go. Let's do that real quick, and I'll show you guys my process of graphing this. So first of all, start with the inflection points. With intercept points, and we did, right? We have 1 at x equals 0, 0. So there's a point there. We also had, now let's talk with asymptotes. There was no vertical asymptotes, but there was a horizontal one at 1 and -1. So we're going to create that. That's y equals positive 1. And then we have another one at y equals -1. All right, so what else we have? We know the function is always increasing. So we know that the function is going to look like this, right? It's always going to be increasing, 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 right? But we also know that the function is concave up. So it needs to be concave up. So therefore, it's going to look something of this form. And then from here, we have an inflection point, and then it does concave down, right? So this is an inflection at 0, 0. So therefore, we can conclude here that our function is going to look sort of like this, and it's always going to be increasing, right? It's always going to be increasing. So there you go. So we are able to graph this function with a lot of detail, and obviously we're going to want to make sure we label our graph right there. All right, so there was another problem here that I want you guys, this is just for practice, so I'll let you guys try the other one by yourself. The other one, I wrote down the detail there, so you guys can kind of see it's very similar to what we done up in the in the process. So please go over this one. I ended up using a calculator for some of the work, where we had to actually find the zeros. I use what we learned in college algebra. Go over that part. I use the calculator to find out the values of the derivative by plugging them into the calculator. All right, so I hope this is helpful. Please let me know if you have any questions. Thank you.